Hello, everyone, and welcome back to your channel of Math and Engineering Made Easy. Today, we are going to see how we are going to graph an exponential function or equation. Well, function, yeah. So, we said last time, let me get a pencil or a pen and say that usually we say y equals some constant a times another constant b raised to a power of x. And we want to plot that for different values of a and b. Okay. Well, of course, you can also add or subtract a constant from that, but that's a different story. If I have something like that, I see that when x equals 0, you get the y-intercept, and in which case it would be y equals a. Because if x is 0, b to the 0 is 1, and you get the y-intercept equals a. But what is the solution for this function? Meaning, when does it cross the x-axis? It turns out that if you set y equals 0, and since a is a constant, the only possible way for b, for any value of b, so that b to the x equals 0, you won't find it. Even if you make x a very small number, like negative 1 billion, you will see that we are approaching the 0, but never crossing the x-axis. So there is no x-intercept for this generic equation, or for this equation y equals a b to the x. There is no x value that, I'm sorry, an x value for which y is 0, unless x is negative infinity, so we don't have that. One more thing, if that equation is a growth, meaning if b is greater than 1, you see that the general shape of my function would go something like that. At negative infinity, it approaches the 0, so the 0 is an asymptote. And if this is the x-axis, and let's say this is the y-axis, this point will always be 0 and 1. As I said, if you don't add or subtract something. So 0, uh, in fact, 0 and a, I would assume, I'm sorry, I was drawing it for y equals b to the x. So this should be 0 and a. Okay? If x is 0, you get y is a. If x is 1, you get y equals ab. So this point, if this is 1, you get 1 and ab. Most of the time, not most of the time, but for many problems, we don't give you a, meaning a is 1. So you get this point is 0 and 1, and this one point is 1 and b. And then it would be 2 and ab squared, 3 and ab cubed, and so on and so forth. That's the growth case when b is greater than 1. But if b is between 0 and 1, if b is greater than 0, less than 1, we say that's a decay. And my function, if it's the same a and b values, it would be a symmetric about the y, so it would pass through this point. And this point 0 and a would be on both. And you see that the y-axis here would be an axis of symmetry, meaning the right-hand side is identical and a mirror image of the left-hand side and vice versa. What else I needed to say? Yeah, if this b get larger, so if I have a c to the x and c is greater than b, then uh, then this equation, or with this plot, will go higher faster. It would be more steeper. So you increase c, it will be steeper. You decrease c, it becomes flatter. You see that? Unless until x is until c is 0, then it would be like a horizontal line, the x-axis, but of course you won't get that. So after understanding these things, the difference between the plotting a growth function versus the decay function, let's take some examples. Like some of them are multiple choice, like in your Regents exam, and some of them also in the second part or third part of the Regents exam when you will have to graph something. Milton has his money invested. Oh, I'm sorry. This was the same. This was from last time, and I just said I'm going to ignore it because it's a continuation. So here is this one, graphing exponential functions. The graph of y equals a to the x. So it's not a times b to the x. No, it's just a to the x, meaning there is we call this b. So when a is 1, you get b to the x. Where a is greater than 0, it contains which one of these points? We mentioned those. Of course, we said the y-intercept occurs when x is 0, so a to the 0 is 1, and you get y equals 1. So when x is 0, y is 1, and that's number 4. The graph of the equation y equals m to the x, or a to the x, it's the same thing. It passes through which point? Notice that when x is 1, remember here, we plotted those. We said 0 and a, in this case, a, I wrote it a times b to the x, right? They write it a to the x. So I don't want you to get confused. We can use any letters. But if a is 1, you get a to the x is b to the x, if a is 1. So this point would be 0 and 1, and this point would be 1 and b, because a is 1, right? In this case, they have, instead of b, they are using m. So they tell you which point here, 0 and m? No, it's always going to be 0 and 1. 1 and m? Yes, 1 and m, because this says 1 and b. So if instead of b they are using m, I will get when x equals 1, y equals m, so 1 and m is the correct answer. When we move to number 3, it says the graph of the equation y equals 2 to the x intersects only the x, only the y, both x and y, neither x and y. Of course, we know it always intersects the y, right? So when x is 0, that's the y-axis, y would be 1. So it's only the y-axis. Number 4, the graph of the function f of x 3 to the x lies in which quadrants? Well, 3 to the x would look something like that, this or that. It doesn't really matter. It depends, how steep it is. But that's the quadrant 1 and 2. So 1 and 2. Which transformation of y equals 2 to the x results in the function y equals 2 to the x minus 2. So after you get 2 to the x, you subtract 2 to get the y. So it's going down 2 units, right? So which transformation? The transformation is 0 and negative 2, meaning the x doesn't change, but the y will go down 2 units. So it's number 2 again. Wow, we have 2, 2, 2, 3 2's. Okay. Teresa is comparing the graphs of y equal 2 to the x and y equals 5 to the x. Which statement is true? The y-intercept of 2 to the x is 0 and 2, and the y-intercept of 5 to the x is 0 and 5. No, both of them will have an y-intercept of 0 and 1, as we mentioned. Both graphs have a y-intercept of 0 and 1, yes, and y equals 2 to the x is steeper than 5 to the x. No, of course, 5 to the x is steeper, right? Both graphs have a y-intercept of 0 and 1, and y equals 5 to the x is steeper. So that is correct. Neither have a y-intercept. No, they do. The graph of the function f of x equals a to the x is shown on the accompanying set of axes. On the same set of axes, sketch the reflection of f of x in the y-axis. That's exactly what we were saying. It's going to be something that looks like that. Okay. State the coordinates of the point where the graph intersect. Of course, the graph intersect always at 0 and 1. We already did that, remember? This one, that one. They always intersect at this point. Okay. Next, now we have to plot. So we can use a calculator and also a table. We can make a table for number 8. Well, there is a quicker way to do it. We know that y equals 0, which is the x-axis, is an asymptote of 2 to the x. But this is not 2 to the x, it's 2 to the x minus 7, meaning I will go down 7 units. And I can just plot this dotted line as the asymptote. Oh my God. I need to have something that is softer, it's not that brittle. So that's the asymptote. Okay, so I can plot 2 to the x and then subtract 7, meaning if I get an x and a y here, I know that an x equals 0, y would be 1, right? 2 to the 0 is 1, but I'm subtracting 7, so that would be negative 6. So this is a point. At x equals 1, 2 to the 1 is 2, minus 7 is negative 5. So at 1, I get negative 5. When x is 2, 2 squared is 4, minus 7 is negative 3. When x is 3, 2 cubed is 8, minus 7 is positive 1. And finally, when this is 4, 2 to the 4 is 16, minus 7 is 9. And of course, the asymptote comes here. And then I will try to go through these points. It goes up fast. And that would be the graph. We'll talk about when we add or subtract or multiply, how we treat that in the graph transformations. I will show you slightly different method than the one you learn at school, but to help you. Okay, on the set of, oh, I'm sorry, if g of x equals 1.5 x minus 3, so that's an equation of a straight line that has a y-intercept of negative 3 and a slope of 1.5, meaning every time you move 1 to the right, 1x, you go 1.5, meaning every 2x, you get 3y. So 2 and 3, 2 and 3, 2 and 3. And this is our line. It's better always to write g of x equals 1.5 x minus 3. And here you write f of x equals 2 to the x minus 7. Okay, determine if f of x is greater than g of x when x equals 4. Here is 1, 2, 3, and 4. This is x equals 4. Which one is higher? F of x is higher than g of x. Justify your x's. Yes. f of x equals g of x equals. F of x at x equals 4, we said it's 9. But g of x at x equals 4 is 1, 2, 3. And you can substitute also. You say uh, when x is 4, 1.5 times 4 is 6 minus 3 is 3. So f of 4, we can write it f of 4 equals 9 and g of 4 equals 3. And you can substitute in the equation, but we already have 4 and 9 here. So that is correct. When we go to number 9, on the set of x's below, draw the graph of y equals 2 to the x from x equals -1. So let's take 2 steps for every one, 2, 3, 4, -1, -2, -3, -4. And maybe because that's faster, we can do 1, 2, 3, 4, 5, 6, 7, 8. We don't care about the negative because we will not have negatives in this problem. So from x equals -1 up to x less than or equal to 3. Okay. At -1, y would be 1/2. 2 to the -1. Remember when the exponent is negative, we say it equals 1 over 2 to the first. 2 to the first is 2, and 1 over 2 is 1/2. So here's 1 point. We know that when x equals 0, I go through y equals 1. We put them in a different color so we see the points. And x equals 1, you get 2. At x equals 2, you get 4. 2 squared is 4. And x equals 3, you get 8 because 2 cubed is 8. You are not going to extend because they want it from -1 to 3. And your graph would look something like that. There is no arrows. It stops here. Will this graph ever intersect the x-axis? No. Justify the x-axis is an asymptote. So it never crosses that. And finally, well, we have 11, so not final. Number 10, on the set of x's, draw y equals 3 to the x from x equals -1. So let's say -1, -2, 1, 2, and it's just still 2. So 3 squared is 9, so we can use ones 1, 2, 4, 6, 8, 10, and that's it. And again, x from -1. At -1, you get 1/3. 3 to the -1 is 1/3, 1 over 3. So you will get a point maybe right here. At x equals 0, you get 1. At x equals 1, you get, oh, I'm sorry, I did, yeah. Yeah. Okay, at x equals 1, you get 3. At x equals 2, you get 9. And the graph would look something like that. Very simple. And there is no other questions. And finally, the last problem says, graph f of x equals 3 times 2 to the x. Huh. Remember, this is like a b to the x. A is 3, meaning when x equals 0, I cross at y equals 3, not at y equals 1. Right? Still, the x-axis is an asymptote, and the interval is from -1 to 2. When x is -1, 2 to the -1 is 1/2, but 3 times 1/2 is 3/2. So if we say this is -1, this is 1, this is 2, so I give myself space. Here I'm going to write this is 2, 4, 6, 8, 10. 12. Okay, so at x equals -1, you get 3/2 or 1.5. So you get this point right here. Then when x equals 0, you get 2 to the 0 is 1 times 3 is 3. So you get this point right here. When x is 1, you get 2 to the first is 2 times 3 is 6. So at 1, I get 6. And finally, at x equals 2, 2 squared is 4 times 3 is 12. And you get this point, and your graph would look something like that. And this would be the graph they want between x equals -1 and x equals 2 inclusive. And that's it for graphing exponential functions. Next session, we will start with logarithmic functions. And I told you, like we said, addition and subtraction are inverses. Multiplication, division are inverses. Square and square root. We haven't yet decided, or we haven't yet discussed the square root function, how we draw it, how we deal with root functions in general, like radicals. But that they are opposite of each other. Exponential or exponents and logarithmic functions are inverse of each other. So every time we learn something new, we find its inverse, so they cancel each other, and we'll see how that, like when you have, a problem like it says 4x equals 12, in order to solve for x, since the x is multiplied by 4, you divide both sides by 4. You apply the inverse operation to cancel the 4 that is multiplied, and you release the x by itself. Same thing, if I have a to the x, and I want to solve for x or x to the a, it doesn't really matter. I will apply a logarithmic function that takes away that exponent and make it like as if it's a linear function. And that's exactly what we are going to learn once we go over the logarithms next time. Thank you very much for your time, and thanks for watching, and hopefully I'll see you soon.